Greetings. Before we start with the trial and error with that equation, just blindly follow a trial and error and see where we could end up. It's good to have a look at this curve and see what does this diagram tell us. You see, it's very difficult to guess that this is the incoming fluid, which is warmer, has a higher temperature, and has a higher pressure than the what already there is inside the tank. If these two mix, would the temperature be somewhere in the middle? We know that the final pressure would be on this line. We already know it. Okay, but will the final temperature be to the left of the incoming steam, or it will be to the right? Will it be warmer or cooler? Certainly, the pressure has to increase and therefore the temperature has to increase. On the other hand, we are mixing two vapors, one warmer and the other cooler. Where would the final point be? It's not easy to just judge by the look of it. What does the first law of thermodynamics, the mass conservation law, and the equation of state tell us? What do they tell us? Is what is possible, what is impossible, and where we should look for an answer. And that is what these equations just do. So just let's try. What we do is we try a point. What I do is I try different temperatures. Different temperatures, say this is the line of 689 kilopascals, 689 kilopascals, and what I do, and this is point I try one point to the left and some other point to the right, read the values for U and V, and see how does that compare with minus 1536. So if I select the point at T equals 478, which is our initial point, find values for U2 and V2, replace it in this equation, and the outcome would be minus 3895.98. So it is wrong. We have to come with this one. Select 450, E equals 450, to learn if smaller value is possible. And the answer would be minus 5162.9. So a smaller value, a smaller temperature is not possible. That is what the combination of mass conservation, first law of thermodynamics, and the equation of state tell us. The equation of state is the properties of steam. You can't just find the correct match for steam at lower temperatures. So go up, and at T equals, I have tried many numbers, but at T equals, let's say 600, the answer would be minus 197.18. So it's something between 450 and 600, and what I ended up with was T equals 548 kelvins, which resulted in U2, your V2 equal 0.36 cubic meters per kilograms, and U2 equals 2759.2 kilojoules per kilograms. These are the two values which we calculate, and now we are in a good position to calculate the mass, the final mass in the um, in the control volume. In fact, here we have just found that if this is 5.66, this value is 0.36, and this gives us the ratio, which is 15.72. This ratio would equal 15.72, and that is the final mass in the control volume. The initial mass is also possible to calculate. Just the result of this ratio, which would be 4.515, and therefore the mass that has entered our control volume would be 11.205 kilograms. And that is the answer that the question has asked us, the problem has asked us. We could also note that the final temperature was 548. This is 4.7. It is on this 478, and that is 548. It has some distance to this one, and it is on this line. A specific volume is 0.36. Look, the final specific volume is 0.36. So it should be less than this one, and it's somewhere near here. So the point would be somewhere here. This is 0.2. And temperature is 548 Kelvin. Look, please note here, we have to draw this line with a very gentle care. Here, Vg is 1.2534. So here, this point, specific volume is 1.2534. What is the specific volume here for point I? It is 0.309. So in fact, we should have given such a slope here that it would end up somewhere like here, far away from four times this distance. We should have to go further right to find the right point for Vg at this point. And that's why when I wanted to draw point 2, which is a specific volume is 0.36, I had to be very careful. It's somewhere here. It is somewhere here. Somewhere between 0.309 and 1.2534. Of course, this point should have been far away to the right. It's a good job here to study some alternatives to this problem and see what would have happened if, instead of telling you that our final point is on the line 689, could our final point be on the line 478? Could it have higher pressure? Could it have lower pressure? Where could it be? Could we have a final point here? We couldn't have a final point on this line. But could we have a final point on this line? Or on higher pressure? Could we have, and this would be higher pressure because if the final point was here, it would have a higher pressure than 689. Could that happen? Still, another point. There is a path here between 1 and 2. Okay, this path, this process happened adiabatically. If it wasn't adiabatic, then could we end up with different points? Could it be possible? What would happen? I have redrawn this curve now just to be more in line with the difference that should happen between point 1 and point I. And the question I want to ask is this. Is it possible? Well, we saw that it wasn't possible to be on the lower temperature side of P689. Is it possible to be on this line, 478? Okay. Is it possible to be on this line, higher pressure? And to calculate it, the story is very simple. What we do is this is our equation, this is also rewritten it. And what we do is to say, well, if our temperature is 478 Kelvin, T equals 478 Kelvin, we try a few pressures. Say after 689, we try P equals 700 kilopascals. And for these two values, we go to tables, and what we get is V2 equals 0.304 cubic meters per kilograms, and U2 equals 2643.6 kilojoules per kilogram. On the same line, you see 700 line is a bit higher, this is 689, 700 would be just a bit to the left. P equals 750 kilopascals, and V2 would be 478, V2 would be 0.283 cubic meters per kilograms, and U2 is 2641.6 kilojoules per kilogram. And if we calculate the left-hand side of this equation with these values, with this one, the left-hand side would be minus 3967.5, and for this one, the left-hand side would be minus 4301.9. What does this mean? We are going farther away from 1536.46. It means that it is as we go further away from here, it will be more and more impossible to have an adiabatic process which ends up here. And that's not far from expected. You see, let's have another look at this problem. Okay, let's have another look. And the story is this. You have a line with 689 kilopascal entering a tank with 138 kilopascal. If the pressure inside the tank comes over 689, then there is no way that the steam from this line would enter this tank. It would be the other way around. In fact, the steam would go out of this tank. I mean, if the pressure becomes equal, if the pressure becomes equal, pressure of this tank becomes equal with this value, with the entering pressure, then the process would stop because there would be no longer any steam going in. And there's no way that the pressure inside the tank would be higher than the pressure of the incoming steam. This has no power to increase the pressure inside the tank more than the pressure it already has. So, in fact, although we could have guessed this very simply, but still, the first law of thermodynamics, mass conservation, and equation of state combined tell us that it is impossible, and the higher the pressure goes, the more impossible it becomes. So we have made a conclusion. You see, the first law of thermodynamics and the mass conservation law already tell us what is impossible and what is possible. Now, we make a second proposition here. And the other proposition is it possible, say, if we found that it is impossible to be on this line, okay, at any point with higher pressure than 689 kilopascal. Is it possible to be on this line, but for a point with a pressure less than 600 kilopascal? That should be possible. And let's see what happens. Say, is it possible to be on a line, say 500 kilopascals? If this is P equals 500 kilopascals, could we end up here? Is it possible to be on this point? Is it possible? And still the equation is this one. And for this point, we have all the properties. We have all the properties because we know the pressure, we know the pressure, and we know the temperature. So we know that P equals 500 kilopascals, and we know that T equals 478 kelvins. Go to the tables and read the values. The values would be V2 equals 0.43 cubic meters per kilograms, and U2 equals 2651.3 kilojoules per kilogram. Okay? Now, put it in this equation and see what ends up. The left-hand side would be minus 2703.6, which is not equal minus 1536.46. What does this mean? It means that for an adiabatic process, for an adiabatic process, it is impossible to cross or to reach point P equals 500 kilopascals and T equals 478 kelvins. An adiabatic process won't cross this point. There should be another term here to balance the equation, to balance this equation. And if we had heat transfer, Q equals minus 1167.1 kilojoules, then we could expect to end up here. With such heat transfer, we could expect to end up here. In fact, this process could have any heat transfer and end up anywhere in this line. It couldn't go any, it could have a pressure higher than 689, but with some heat transfer, and this is losing heat, with losing some heat, it could end up here. But if it was adiabatic, what would happen? Could it be adiabatic? I mean, the adiabatic process goes over this line. Okay? So the adiabatic process could cross the line P 500 kilopascals at some point. It should do. I mean, there could be Q equals 0, okay, and say for a pressure of 500 kilopascals, we should be able to come to some point, to some temperature, to some point on this line. And it should be possible. And let's see if it is possible. And what I did was to try this. So I tried with, you see, my temperature is 478, and this is 548. I expect to be somewhere in between. So I tried, and I write it down with a different color. Is it possible? The question is it possible to cross the P equals 500 kilopascal line with an adiabatic process? And the answer is why not? Just the same as we could do an adiabatic process and reach the 689 kilopascals, somewhere in the way we should have crossed the 500 kilopascals. And that's what we did. So what we do now is to try values between 478 and 548. And what I ended up with is that if we try T equals 525 kelvins, then we would reach a V2 equal 0.476, and U equals, in fact, this won't be 2. This won't be, let's call these values be 3 and U 3 and T3, which would be end up here for this point 3. And for this one, let's call this one point 4. And so this would be U4, V4, and U4, and U4 would be 27, 26.9. And the left-hand side of this equation without Q would be minus 1543.4, which is close enough with this one. So as you see, with all points on this line are possible for an adiabatic process. All points under this P equals 689 kilopascal pressure line are possible, but with some heat transfer. We should have some heat transfer to end up on a point underneath this line. Above this line, everything is impossible because basically, simply, we are mixing two pressures, and we cannot end up at a pressure higher than that. If the pressure if the pressure inside the tank is higher than the pressure of the input line, then simply steam would go out of the tank and it won't enter. Now, there is a adiabatic line, and on this line, there is a point which crosses every pressure line. So the final conclusion is this, that every law of thermodynamics and the equation state tell us what is possible and what is impossible. The second law does this job quite professionally in a very different level. But even without that, the equation in the laws, you see, this equation, which we try to satisfy, tells us what is possible and what is impossible. It was impossible without a heat transfer, and it was possible with a heat transfer. Okay, well, thank you very much for your attention, and I hope that you learned different possibilities of these two laws, mass conservation and the energy equation. Cheers.